In this video, we're going to continue our previous one by looking at some review problems. All these problems have something to do with integration. So this one says, suppose the rate of sales of a given product varies with time, and let R of t be the sales rate in items per year, and let t equal 0 correspond to January 1st, 1995. What is given by 0 to 1, the integral from 0 to 1 of R of t dt? Now notice, since R of t is a rate of change in total sales, it is the derivative of the total sales function. Therefore, by the fundamental theorem of calculus, this integral will represent the change in total sales from time 0 equals t to t equals 1. In other words, the integral represents the total sales during the 1995 calendar year. The next one, we're going to take a bicyclist pedaling along a straight road with a velocity v. And we have this here. We'll take positive velocities toward the lake and negative velocities away from the lake, and they're 5 miles from the lake. Okay, so let's see if we can kind of make some sense of this. The x-axis here is the t-axis. It's time and hours. So this is a 1-hour trip from time 0 to time 1 at the end here. And these are miles per hour here. So let's just see if we can get some what's happening here. So these are velocities here. So the highest velocity is right here when they're going the fastest away from the lake, and they're going back toward the lake here, and this one here. Now, notice that if we have miles per hour for the vertical axis and hours here, when we multiply those, like to find one of these areas in one of these little rectangle or grids here, grid rectangles, we'd be multiplying miles per hour times hours, we get miles. So areas on this graph represent miles out in reality for the cyclist. So positive areas here represent areas above the x-axis, in other words, represent distances traveled away from the lake, and then these are back toward the lake. So notice that the cyclist starts here, goes away from the lake, speeding up. At right this point, they're going the fastest away from the lake. They start slowing down, but still moving away from the lake. At this point right here, which is at 1/3 of an hour or 20 minutes, the cyclist turns around and goes the other direction, heading back toward the lake. Somewhere in here, it's hard to say exactly, there'll be a place where this area is matched by an area right in here, maybe in here somewhere, and they're back where they started, 5 miles away from the lake, and then they continue toward the lake. Now, if this area here, of course this area here is bigger than this one here, so they end up closer to the lake than when they started. If it turns out that this area down here, the one up here minus this one down here, is, if that's smaller than -5, then they actually went into the lake or over the lake in a bridge or something. Whereas if this is not quite -5, when you put this and this together, then they didn't quite make it back to the lake. So to compute these areas, since we don't have a formula for this, we need to approximate with some kind of Riemann sum. And so the way to do that on each piece is to take this and say on this piece here we want to draw a rectangle. Okay, maybe, I don't know if that may be a little high. But we want to draw it in such a way that this area right here is going to be completely balanced by this one here, maybe just a teeny bit lower than what I did there. So don't necessarily automatically go for left, right, midpoint, or trapezoid, or or whatever to draw it, but just try to draw somewhere to balance these parts here and here, and so that gives us a rectangle that's going to be of the average height for that interval. And you want to do this for each interval that we're working with, and this is going to help make us work on this this way. So each interval is looks like 0.05 hours, or about 3 minutes. Okay, and so we need to work that out. So I did that, and when I did that, I found out that I approximated this first area to be up to about here, to be about 8.3, and she started at 5 miles away, so she ended up 13.3 miles away from the lake at that point, and that's where she was furthest away from the lake, was actually right here where she turned around at 20 minutes into her trip, a third of an hour into her trip. We'll come back here. Where does she end up? Where's her closest point? The closest point is all the way at the very right end of the graph, 1/3. Wait a minute. I'm not sure I've said the right thing here. Positive take her toward the lake, and negative takes her away from the lake. I think I said that wrong just a minute ago. So she's starting 5 miles away. This takes her toward the lake. Okay, and then this takes her away from the lake. So if that's the case, let's see what happens here. So this should then, okay, with that in mind, that area so she's going away from the lake. That would put her the closest was about 3.5 miles away, and she's farthest away at the end. So what I'm saying here is I'm estimating, okay, we're saying that we're estimating this to be about 1.5 miles for this area right here. Okay, and so we would need to do that by approximating the area, the heights of each of those little pieces, multiplying by 0.05 hours and getting a distance for each of those. And so we would add that up, and I've estimated it to be about 1.5. Okay, and that's closer to the lake, so that would be 5 minus 1.5. Okay, and so that gets her that close to the lake. Then we add on this area, but if we take this area here minus this one up here, we end up with about 8.3 miles. Add 5 to that, she ends up at 13.3 miles away from the lake. So the closest she got was about 3.5 miles. She turned around, went the other way, and ends up in the opposite direction, about 13.3 miles from the lake. Number 11, a certain bond is guaranteed to pay a flow rate of 200 plus 25 T dollars per year for 10 years, where T is the number of years from the present. Assume that the money can be invested at an interest rate of 6.5% compounded continuously. What's the total value of the income stream? Well, since that's a flow rate, you just add up that flow, that is, integrate that flow, for the 10-year period from 0 to 10, and that's, we can work that out, because that's an easy one to find an antiderivative of, but we can also use just the function integrate on the calculator, and either way, you're going to get about $2,250. And the present value of an income stream is you take the flow rate times e to the k minus kt, where k is the interest rate that you can get if you compound it continuously. So notice that k is 0.065 here. So we just multiply that flow rate, 200 plus 25t, times e to the minus 0.065 t. That should have a t in it. .065 t, and then integrate that, and I did put the x in it here like I should have, and so that's $1,555.58. Now what this means is, what these two numbers mean is that if I actually had this money flowing in continuously into, say, a bank account, and I just left it there for 10 years, but this bank account was not paying any interest, then at the end of the 10 years I would have $2,250. But if I were to, one thing I could do is invest the money. So if I would take the money and put it into account and invest it as much as invested each time, then I would make a certain amount of money at the end. Okay? Now, I could invest right up front, just take a flat rate of $1,555.58 and invest it in this account and let it just earn interest. And I would end up with the same amount at the end, higher than the $2,250. It would be that plus interest. That's called the present value of that stream. Okay, next we're going to look at a supply and demand situation. Supply and demand curves. Now remember, supply and demand are both a relationship between price and quantity. They're actually both one-to-one functions, so you can actually write it as the price is a function of the quantity, or quantity is a function of the price. But here we're listing the price as a function of the quantity, and that's the way you want to do it for these particular ones. Okay, so Q is or X is Q, or the quantity, and we put the price on the vertical axis. So if we do it that way, we want to graph these two functions, and certainly quantity and unit price are both positive, so this is a first quadrant graph. Notice that this first one starts at 650 for the highest point, so I know my y has to go up to at least 650 to see this, and I just kind of maybe a little guess and check, figure out to where this, see where this kind of comes down to the x-axis here, and take a good look at this, and this gives me a decent window. Now notice one of these functions will always be decreasing and the other one's increasing. The demand curve is always decreasing because as you increase one of the variables, the other one decreases. So as you increase the price, people will buy fewer of them. The consumer will demand fewer items. So that's a decreasing function. Or as you increase the demand, the demand will increase when the price goes lower. So this is a decreasing function. Supply, on the other hand, is an increasing function because as you increase the price, the producers will collectively want to supply more items. Also notice that the supply curve typically, well, both of them typically intersect the vertical axis, if it's the unit price axis, at the positive here, because this is saying they will produce zero. The producers will produce 0 items at that particular positive price. There is a price below which they will not produce any items, and that's that intercept there. So we have this. Now, if you leave this alone in a free market economy and just let things go, you'll reach what's called the market equilibrium point, which is where these two things cross. And so that's the intersection there, and I can certainly do this numerically just by calculating the intersection. Of course, what I'm doing is actually solving this system equation. Since they're both solved for p, I would put the 650 minus 4x minus x squared equal to the 64 plus 5x plus x squared, and solve that maybe using the quadratic formula or something like that. But I can also do it numerically by just doing a calc intersect, and this gives me an x and a y. I'm going to call that x value my quantity q, q0, or to store it as q in the calculator, and y I'm going to store it as p in the calculator, and that's my p sub 0, our price. So this is the market equilibrium price and quantity. Now how much money actually changes hands? Well, we would see that on the graph as a rectangle. Let me draw it in for you. It'll be a rectangle with height. So on the graph, this is the point we're looking at. Here's the market equilibrium quantity. Here's the market equilibrium price. And of course the area of this rectangle right here is the amount of money that changes hands. Notice that the y values here are in dollars per item and the x values are in items. So when you multiply to get an area, you're actually just getting dollars. So dollars in reality are areas on this graph. So the area of that rectangle is the amount of money that actually changes hands if we're at the market equilibrium point. And so that's just our price times our quantity, which turns out to be $5,472.89. Now, find the consumer surplus at the equilibrium point. Okay, consumer surplus is, and then illustrate it. So this red here is the consumer surplus. You take the difference in the demand curve, it's the area under the demand curve that's above that part that's being actually changed hands for the market equilibrium. So if we integrated the demand curve, we would get it all the way down to here, but what we need to do is we need to subtract off what's in this rectangle right here. What's left is the red part, which is the consumer surplus. So we're just going to integrate this, and so since I just need a decimal answer, I'm going to use the numerical integration. So it's function integrate. That demand curve was in y3, the way I did it. So that's the function integrate y3 with respect to x from 0 to 15.01. Then I'm subtracting off the area of that rectangle, and what I'm left with is the red part there, $2,705.76. That's the consumer surplus. Now, similarly, so how do I think of that? I think of that as what the consumers think of as the bargain they get. If every consumer was buying the item for the maximum they would be willing to buy it for, you would actually make money all the way up to here, and it'd be the area of that big shape across there. But in fact, only this part down here at the bottom is what actually gets spent. So collectively, the red is what the consumer thinks of as just a bonus. Now, the producer, on the other hand, gets a bonus too, and it's by the blue area here, which is our rectangle minus the integral. And so that is given by this amount right here in blue. And so we can do that as that area of that rectangle minus the numerical integral. And finally, one more problem. Suppose that the marginal cost for a product, which is C prime of x, we know, is 60 times the square root of x plus 1, and its fixed cost is $358, and the marginal revenue is 86x. Find the profit or loss from a production of 8 units. So we got to reconstruct the profit function from the marginal cost and marginal revenue. So remember that, marginal profit, P prime, is marginal revenue, R prime minus C prime. So if I take R prime minus C prime, that's 86x minus 60 times the square root of x plus 1, and then integrate that over the time period, I'll find the change in profit, or the, and since we're starting at 0, this will be the total profit from those 8 items. Okay? The fixed cost, then we have to, this will be the additional profit, but we started with a profit of negative 358, which was our fixed cost, so we need to subtract that off. Okay? And so this will give us our profit function, and we can just do that numerically, or I could find an antiderivative, but we go with numerically function integrate 86x minus 60 square root of x plus 1 with respect to x from 0 to 8, subtract the 358, that's $1,354 of profit.